and what type of weight vectors they are? They are real valued weight vectors. Okay, so here see that hypothesis space is represented once again with a capital H here. That capital H, what it is exactly? Just now I told that it is a weight vectors. Okay, set of weights, set of weight vectors. So it is represented as a W arrow mark. So here the complete hypothesis space is full of a small letter or lowercase letter W's. So here W's are nothing but weights. And what this weights belong to? This weight is belonging to one more set, that is set of weight vectors. Set of weight vectors is represented by this symbol, that is a capital R like symbol, some um, symbol, mathematical symbol R to the power n plus 1. Okay, so which is nothing but set of weight vectors. To these set of weight vectors, this weight vector is also belonging to. Okay, so here H is nothing but hypothesis space where we are getting set of weight vectors. Okay, so here, so let us go to next topic, that is representational power of perceptron. So just now we have seen the representation of artificial neural networks and representation of perceptron. So now we will see a little more about these perceptrons representations. Okay, see, we can imagine this perceptron as a surface. Just imagine. So we can imagine this perceptron as a surface. Which surface? See, we can imagine this perceptron as a hyperplane decision surface. Remember this word, technical word, hyperplane decision surface. In next class I will show you how with one real surface like example. Okay, just now you imagine it as a perceptron is just like a hyperplane decision surface. It is why it is decision surface I will tell you later. You just imagine this perceptron like a, how exactly this perceptron looks like a it looks like a surface. Okay, you can consider it as just like a white paper, surface of a white paper. Okay, so here this perceptron is representing some surface, and that surface is technically called it as a hyperplane and decision surface. And where it is this surface is present, this surface is present in some space of examples or some space of instances or some space of some points. So what's the dimensionality of that space? That dimensionality is a n dimension. It means that it is multi-dimensional. It may be one dimensional, two dimensional, three dimensional, or four dimensional, or n dimensional space it is. Okay, so even if you consider it as a three-dimensional, okay, for example, if you are considering three-dimensional space of instances, you can compare it or you can assume it as just like a bread which is present in a bakery. Okay, in a bakery I think you have observed the bread. So before making it into or before cutting it into a slices, how that bread looks like, in the same way you just imagine this n-dimensional space of instances. Inside this instance only, the perceptron is present in the form of a surface. Okay, it means that when we cut the bread in the form of slices, n number of slices, one slice is called as one perceptron. One slice is called as a surface, hyperplane surface. Are you imagining now? So this is how exactly this perceptron looks like. Okay, so completely this everything is imagination. Just imagine that this perceptron is as a surface of n-dimensional space of instances. And already I told you this perceptron gives us some output, only two possible outputs. One is a positive one or plus one, one more is negative one, that is minus one. So when it gives us plus one, already I told you, for the instances which are lying on one side, it means that here the multiplication of weights and inputs is greater than 0. Okay, so one side of this hyperplane surface, for one surface it gives us plus 1, for other surface it gives us the output as minus 1. So minus 1, what is indicating? The minus 1 is the instances which are lying on other side of our surface, hyperplane surface. Okay, so here let me to show you in this figure 3.3 how exactly it looks like. See here. Okay, see, this is a one surface, and this is a one surface, other side of the surface. Here one straight line is there, no? You just imagine this straight line as your bread slice. Okay, bakery bread slice, one slice, or you can imagine it as a your paper. Okay, white paper. So one side of this paper contains only positive training examples, and another side of this paper contains only negative training examples. Is it clear now? So here some training examples are there. So some training examples are positive here, some training examples are positive here, and here some training examples are negative and negative. So here we cannot make two partitions with one straight line to make a separation between these positive or negative training examples here. Okay, this is a second possibility. So such type of examples are called as non-separable training examples. Remember this word, non-separable training examples. Okay, but these training examples are separable training examples. Separable training examples. Okay, just for your understanding purpose I have shown you that diagram. So for one side of that surface we get the output as 1, for other side of that surface we get the output as -1. So the equation for this decision hyperplane, so decision, why it is called as decision? Because we have to take a decision about training examples whether it is positive or negative, so that we called it as a decision hyperplane surface. Okay, so decision hyperplane equation for this decision hyperplane is a w into x is equal to 0. Just remember this one, w into x is equal to 0. It means that here the multiplication or product of weights and inputs is exactly equal to 0. It is not greater than 0 also, it is not less than 0 also. If it is greater than 0, then the output of perceptron will be +1. If it is less than 0, then the perceptron output will be -1. Now since the decision surface is a neutral, so we can call it as a the product as a 0. Okay, so of course some sets of positive training examples are there, some negative training examples are there, so where we cannot make a separate portion for such type of training examples with the help of this hyperplane. Such type of training examples are called as linearly non-separable training examples. Linearly non-separable training examples, but the training examples which we can make a separation for two types of training examples. First type of is a positive, second type of is a negative, right? So if we can make a two separate partitions for these training examples, or we can separate these training examples with one straight line, then that training examples are called as linearly separable training examples. Okay, linearly separable training examples and linearly non-separable training examples. Just remember these two words. Then here single perceptron can be used to represent this many Boolean functions. It means that these perceptrons, whatever the perceptron is telling you, so that is artificial neural network. This artificial neural network. See, this perceptron can be used to represent these many number of Boolean functions. So Boolean functions means what type of functions? So already you know these logical functions like and, or, NAND, NOR, XOR, such type of functions. These are Boolean functions, right? So here we can represent these Boolean functions with the help of these perceptrons also. Okay, because the perceptron output itself is a in the form of boolean, either positive or negative, right? The output of a perceptron has only two possible values, either plus 1 or minus 1. So because of this nature only, this perceptron can be used to represent the boolean functions also. So what type of boolean functions? And or XOR, nor, NAND, nor, such type of boolean functions we can represent with this perceptron. For example, if you consider this boolean values of plus 1. What is the boolean value of plus 1? Obviously it is a true. And what is the boolean value of minus 1? Obviously it is a false, right? So here, if we assume these boolean values as a true and false, then there is one method to use this two input perceptron. Two input perceptron means, of course, our perceptron can accept n number of inputs, right? X1, X2, X3 up to Xn. So here, for simplicity, we have considered only two inputs, X1 and X2. So here we are going to represent this perceptron. We are going to use this two input perceptron to represent one boolean function. Okay. See, this two input perceptron is trying to represent one boolean function, that is AND function. Okay, here we, for suppose, for example, we have set or we have assigned minus 0.8 to this weight threshold W0. Okay, just now I told that W0 is nothing but threshold, and one value is there, that is minus 0.8, and W1 is 0.5, and W2 is also 0.5. Okay, so why sir only W1 and W2? Just now I told you we are using only two inputs in our example, x1 and x2, and their corresponding or respective weights will be obviously W1 and W2, and both of them are equal, that is 0.5 and 0.5 only. So now if you multiply this W1 with x1, and if you multiply W2 with x2, I don't know what is the value of x1 and x2. Okay, we are just focusing on weights here, W1 and W2. When we multiply W1 with x1 and W2 with x2, and we take the sum of these two terms or multiplications, then we will get the output some value, and if that value is greater than 0, then output of our concept perceptron will be plus 1, and if the sum value is less than minus 0, then output of our perceptron will be minus 1, right? So here the perceptron can be also used to represent one more boolean function, that is OR. Okay, so we can represent OR boolean function also with our perceptron. So two input perceptron. Okay, so here here that threshold value, we are just modified it to, or we have just assumed it as uh, minus 0.3. Okay, so these all things, don't worry or don't bother about these all values, sir, why it is a minus 0.8 minus 0.3 and all those things. Just we have assumed some values here. Okay, in detail we will get into these weights and x1, x2, xn and all those things, how to do these all calculations in the next topics. Just for your idea, I am telling you the main concept is here nothing. Perceptrons can be also used to represent the Boolean functions. That's all. So it may be AND, it may be OR. Okay. So similarly, here let us see the truth table of this AND operation. So if your input is x1 and the second input is x2, then apply that AND operation on all both of these two inputs, x1 and x2. This is nothing but the truth table of AND operation. Since we are representing AND operation with our perceptron, we are going to consider the truth table of this AND operation. Okay, see the beauty of this perceptron, just you have to give your attention, you have to concentrate here, that's all. See this and OR operations, what happens, what is the nature of these and OR operations? Here I have written for your understanding purpose in bracket. In AND, what happens actually, when we get the value as a true as a output, when we get the output true means when both the inputs are true, right? So here I have written when both the inputs x1 and x2 are true, then only we get the output as true. You can observe here. This is a true, this is a true, and then only we get this true. So in remaining all three cases, the output will be false only. Why? So among the two inputs, only one input is true. Here also only one input is true. And in first case, none of the inputs are true. So this is the nature of AND, right? And similarly, what is the nature of OR function? Here in OR function, any one among these two inputs can be true. Okay, so if any one of these inputs is true, then output will be true, or that result of OR function will be true. This is the nature of OR function. So here, because of that only, and OR functions can be viewed as a special cases. Okay, special cases. And what is that special case? Just remember this word, just very interesting, very nice word, that is M of n. M of n. What is that M of n functions? M of n functions. Such type of functions like and or functions are called as M of n functions. Why it is? It means that out of two inputs, okay, here you just imagine that this n is nothing but it is a number of inputs. Out of two inputs, okay, out of two inputs, how many number of inputs should be true to make the result true, okay, or to make the output true? Okay, I hope you are understanding. If it is the case of and, both the inputs should be true, correct? So out of two inputs, both two inputs should be true. That is nothing but this part I am talking about. Okay, so both the inputs should be true, then only it is a true. Similarly, if it is a case of or operation, or function, any one, it means that out of two, any one input should be true to make the result or output as a true. So here, such type of functions, and function and or functions, are called as M of n functions. M of n function means what is this n and what is this m? N is a number of inputs. Out of these number of inputs, how many inputs should be true? So here in AND case, both two inputs should be true. In OR, any one input can be true. So because of such nature of these functions, we call these and or boolean functions as M of n functions. Okay, see, so that is a functions where at least m of these n inputs to the perceptron must be true. At least m of inputs, at least m number of inputs. In or it is 1, in and this m value is 2. Okay, so this is the thing here. So let us go to next function, that is our function. So what is happening here? Here n is equal to 1, just now I told you, right? In AND function, m is equal to n, because just previously only I told you, if two inputs are there, both the inputs should be true, right? Because of that only, here m is equal to 1 in OR function and n is equal to 2 or n is equal to n in AND function. So the truth table for this OR function I have written here, right? So here, so whenever one value is true, whenever at least one value is true, the result will be true, true, true. Okay, so because of this nature, so here any of these boolean functions which are m of n functions, right, and or is easily represented using the perceptron. There is no any difficulty. How we can represent these functions with the help of perceptron? By setting or by some assigning some values. Which values? Some input weights. Okay, by setting some input weights. So some values we have to assign to these weights, and that value should be same. That value should be same value, that is 0.5. So for example, in previous example, because of that only I told you W1 as well as W2 is both of those weights are 0.5, 0.5. If the weights are same, If the weights are same, then it means that it will be very easy for us to represent this and or operations with the help of this perceptron. Okay. So and also what we have to set and also what we have to assign to the weight W0, it is accordingly. So if you go back to this example, here you can see both W1 is also 0.5, W2 is also 0.5. So when this W1 and W2 are 0.5, according to these two weights, W1 and W2, we can adjust the weight value for this W0. Okay, we can adjust this threshold, that is W0. Okay, so here you can see here we can set the threshold W0 accordingly based on W1 and W2. Okay. See, this perceptron can represent in fact all basic or primitive Boolean functions like and, or, and not. Just now we have just shown you how to represent the and how to represent the or. Similarly, perceptrons can be used to represent the NAND also and NOR also. But there are some other Boolean functions are there which cannot be and never represented by this perceptron. Oh, what type of functions these are? The functions like XOR. XOR cannot be represented with the help of a perceptron or no any perceptron. No any perceptron can represent this XOR function. Why? Because of its nature. So that XOR value will be 1. It means output of this XOR will be 1. That is nothing but true. If and only if this x1 is not equal to x2, it means that both the inputs should have different values only. Then only this output of this XOR is a true. So I am talking about these two cases, this one and this one. If you observe, the output of this XOR function is true only when both the inputs are not same. If both the inputs are same, then it will be false, right? So because of this nature, it means that we cannot make a clear separation for these training examples in our perceptron. So we cannot represent this X on with the help of this perceptron. There we had one clear idea for particularly for a true output of and or. But here, because of this nature of XOR, we cannot represent it with the help of perceptron. Okay. So here one word already I told you. Note that the set of linearly non-separable training examples shown in this figure, that is 3.3, which is corresponding to XOR function. So here in this figure, see, I'm talking about this diagram below. Okay, see these whatever the training examples are there, these training examples are corresponding to XOR operation. And here we cannot make a separation for these positive training examples and negative training examples with one straight line. Okay, we cannot make two partitions here for these training examples. But here we can make two clear partitions because all those training examples are belonging to one side of this straight line. Okay, so all of them are positive, all of them are negative. So we can make a separate, we can make a separation for this training examples as a positive and a negative. But in this case, the diagram we cannot make it. So because these examples are corresponding to XOR operation, such type of examples or Boolean functions we cannot represent with a perceptron, but these are represented with the help of and or Boolean functions. Okay, so let us move to next slide. That is also very interesting here. See the ability of this perceptron, the capacity of this perceptron. What is the why? What, in terms of what? The ability or capacity of this perceptron to represent these Boolean functions and or and NOR. is very very important because every Boolean function is represented by some network of interconnected units. Very very important word it is. Because of that only I made it bold. See, this every Boolean function can be represented in the form of network of interconnected units. What is this network of interconnected units? So one clear picture should come in front of your eyes. That is nothing but I am talking about an artificial neural network. Okay, so I have already shown how exactly that artificial neural network looks like, right? So input layer, output layer, in between input and output layer, hidden layer, and each layer contains some units, right? And these units are connected with some arrow marks or some edges which are represented inputs and outputs to the units, right? So here every Boolean function, it may be and or and nor. So every Boolean function can be represented in the form of this artificial neural network. It means that it is nothing but it is a perceptron, right? So because of that only again and again I am telling you perceptron can be used to represent these Boolean functions. It means that artificial neural network can be used to represent these Boolean functions. In contrast or in opposite direction, in other direction, you can say, you can tell it as Boolean functions can be represented as some artificial neural networks. Boolean functions can be represented as a perceptron. Boolean function can be represented as a network of interconnected units. Network of interconnected units is nothing but what? It is artificial neural network only, or it is a perceptron only. Okay. So here the ability of this perceptron to represent these Boolean functions is very very important. And in fact, this every Boolean function can be represented with some network of some network of perceptrons, right? So set of perceptrons, network of perceptrons with only two levels of deep or depth. Two levels of deep. Deep means what here? It means that there will be only two layers. There will be only two layers. One layer is getting some inputs, and the output of this layer will be the input to next layer or next unit. Okay, in which these inputs are fed to the multiple units, right? Inputs are fed to the multiple units, and the outputs of these units are again input to the second and final stage. That is, this is the final stage and the second stage. So this is the first stage. So here we are calling it as a depth is a 2. Depth is 2 or 2 level depth, 2 level D. So one method is there, one procedure to represent this Boolean function, that is nothing but we can represent these Boolean functions in the form of disjunctive form. Disjunctive form. So, like, are you recalling this word? Whether you have heard this disjunction word in previous module? Of course, you have heard it because I told you in the first slide or first class of second module when I started the decision tree learning. Okay, so because the decision tree itself is a distinction of conjunction of constraints, right? So here also we can represent these Boolean functions in the form of a distinctive form. Disjunctive is nothing but OR operation, right? So here it is a nothing but disjunction of a set of conjunctions of inputs. Disjunction of conjunctions of inputs. Okay, so here there is an AND operation between these inputs x1 and x2 and x3 and x4 like this. And is there in between this x1, x2, x3, x4. And these all and operations are there. Like this, many other sets are there. So these all ands are disjuncted. It means that we are putting OR operation in between these all and terms. So then it will be represented as a disjunction of conjunction of inputs. Okay. So just recall your decision tree, then you will get this. Okay. See, these in the AND operation. In the AND operation, if we negate the input for this AND perceptron, then it will be NAND perceptron, right? So we can easily negate the input of AND perceptron. Okay, this input can be negated simply how by changing simply the sign of that corresponding input weight. Okay, just change the weight of the sign of weight then that and input will be negated. Okay. See, next topic is that is a perceptron training rule. Perceptron training rule. See, this perceptron training rule is a very very important topic for your exam because just now I told you the main challenging task in this module is finding the weights, finding the weights because obviously somebody will give us the inputs x1, x2, x3, no problem. But our task is to find or determine or choose or to learn the weights for these inputs because we have to make the combination of weights and inputs, right, to get the output of perceptron because output of perceptron itself is a multiplication of weights and inputs, that is a w vector into x vector. W is a weight vector and x is a input vector. It is a set of weights and set of inputs, right? So here we are going to do that only now. So actual task only we are going to learn now. That is, we are going to find and we are going to determine the weights and that algorithm or whatever the rule we are using, that algorithm is called as perceptron training rule. Just remember this word or heading, very very important. Okay, perceptron training rule. See here, even though we are interested in this learning or constructing networks of many interconnected units, okay, so what it means, it is nothing but we are interested in Boolean functions, or we are interested in constructing an artificial neural network, or we are interested in constructing a perceptron. Okay, so first let us start our task by understanding how to learn, how to determine, or how to choose these weights for a single perceptron. Okay, first we should understand it because x1 getting x1 x2 value or input values is not a difficult task. Getting a value for these inputs, okay, getting a weight values for these inputs is itself is a very important. Okay, here exact or actual learning problem itself is a determining the weight or choosing the weight. And since the weight is represented in the form of vector, we should not call it as a weight vector, we should call it as always as a weight vector, weight vector, weight vector. It means it looks like a or array, or it looks like a W, above that W, one small arrow mark. Okay, it is means representing it in the form of vector representation. Weight vector, it means set of values are there. So it may be white boxes, blocks, or black blocks. White block indicated as a positive weight, as I already told in just today's morning class also, as well as the previous class, right? And similarly, black blocks represent or indicate the negative weights. Okay, positive weights and negative weights. So these weights are causing our perceptron, or it is making our perceptron to give us the output in the form of plus 1 or minus 1 correctly or exactly. So for each and every given training example. Okay, so why this is a training example? It means it is a positive training example or a negative training example. If you want to classify it, so our perceptron should give us the output in the form of plus 1 or minus 1. So to do this one, we have some algorithms. Okay, to solve this one, we have some algorithms, and here in this model, most commonly used algorithms are two algorithms we have for this purpose. Which purpose? To find out the weights, we have two algorithms. The first algorithm is called as perceptron rule. Just remember it. Perceptron rule. Okay. So this is one training rule. Perceptron training rule. Second algorithm is called as delta rule. Okay. Delta rule. Just remember these two algorithms. Perceptron rule or delta rule. So both of them are very very important for your exam. Okay, see perceptron rule, delta rule. First we will see this perceptron rule. This both of these rules are nothing but they are refined form of our earlier rule what we have already studied in module 1. I hope you remember this term LMS. Okay, so LMS rule already I told you, right? So these are refined or extension of this rule only, perceptron rule and the delta rule, or they are versions, different versions of this LMS rule only, what we have already studied in the first module for evaluation functions, that is evaluation function like VCAP, function approximation, or V, right? So evaluation function was represented as V, right? Then it was refined it as a approximate function, approximate, that is V cap. So during that topic, I explained this LMS. So these perceptron rule and delta rules are also, these are just other versions of this LMS rule. Okay, so these two algorithms are very important for your exam, and these two algorithms are giving us some guarantee. What type of guarantee they are giving us? They are giving us guarantee that they are converging. It means that they are moving, they are meeting, they are achieving somewhat different acceptable hypothesis. It means that nothing, these both the algorithms are giving us one guarantee. That guarantee is that so these algorithms will give us some acceptable or correct or exact and suitable hypothesis as a output. And what is the output of these algorithms? Obviously, the main purpose of these algorithms is to find out the weights or determine the weights or weight vectors, right? So here hypothesis is nothing but what here? Hypothesis space contains a small w, already I told you. Hypothesis is nothing but a set of weight vectors. Okay, so here, so these algorithms are giving us some guarantee that definitely I give you some hypothesis as output, and that hypothesis will be acceptable. Acceptable means correct hypothesis, and that hypothesis is nothing but definitely it is a weight, it is a weight vector. Okay, so this type of guarantees these two algorithms are giving to us. And these algorithms are again very important to these artificial neural networks, because these algorithms are going to give us some basis or some foundation for our networks of many units. Networks of many units means what? Networks of many units is nothing but it is artificial neural network only. Okay, or it is a perceptron only. To construct these artificial neural network, these algorithms are giving us some basic knowledge or foundation. Okay, because of that only these two important these algorithms are important algorithms. So there is one method, one method is there to learn or to find out these acceptable weight vector, or to get this weight vector is to begin with the random waves. Okay, so general idea I am giving you now. In the next we will see exactly that perceptron rule and delta rule. Okay, so now right now I am discussing the first one, that is perceptron rule. Okay, in perceptron rule what we do actually to get the weight vector as output. Okay, so first we start our algorithm with finding or okay, see, we are starting our algorithm with one search process. That search process is it is searching some random weights. It means randomly we are searching some weights, and slowly in every step, in every iteration, iteratively we are applying our perceptron. We are applying our perceptron is what? We are applying our neural network to each and every training example now onwards. So at the beginning, we chosen weights randomly, but however some time consumes, some after some time we go little bit specific and particular. Okay, now we are not interested in random weights, we want some particular weights in which we are interested. Okay, so for every time again and again we apply this perceptron or neural network for these each and every training example. And then what we do in third step, we modify or we update the perceptron weights whenever it misclassifies an example. It means that if one positive training example is there, by mistake if it is telling us it is a negative example, or if it is a negative training example and our perceptron is classifying it as a positive training example as a wrong output. So if it is doing like this, if the perceptron, if the system is misclassifying it, then we have to modify or we have to update. What we have to update? We have to update these weights. Which weights? Perceptron weights. Okay. So here, uh, first thing is we have to start with our some random weights, and again we have to apply this perceptron to each training example. And if our perceptron is not able to classify these training examples as a positive or negative correctly, then we have to modify our weights, which I have already got with the random search. Okay, this is the three steps. This is the main funda behind this perceptron rule. That's all. Okay, so now once again that perceptron rule contains one more rule, that is sub rule, that is update rule, because here it is there in second step, right? In first step we got some random weights. In second step we are applying continuously perceptron to our training example, and if our training examples are classified wrongly by our perceptron, then we have to modify or update our random weights, right? So that update rule, we call it as a update rule. How to update and how to update modify these weights we will see now. So simply this process is repeated. Okay, these three steps are repeated again and again, iterating through these training examples. It means that for each and every training example we are applying this one. Then many times as needed, until this process continues until this perceptron is able to classify our training examples correctly. Okay, so then weights are modified or updated if that perceptron is not classifying training examples correctly. So because of this updation or modification only, we call this rule as a update rule also. So these weights are updated at each step according to the perceptron training rule. See, according to this perceptron training rule, now we are updating or modifying our weights. So this perceptron training rule has one more rule, sub rule, that is called as update rule. Okay, so which revises or modifies or refines or updates this weight wi which are associated with our input xi. Okay, according to this rule, that update rule is represented with this equation. What is that updation rule? Already some weight is there, we are updating that weight and we are getting one new w. Okay, so within 5 minutes this session ends. In the next class I continue. Just to give your attendance. Sridhar, Aishwarya, Akshata, Aniket,
Yes, sir.
Pratibha, Saurabh, Ankita, Ankita Patil, Ankita Rupale,
Present, sir.
Geeta, Jyoti,
Present, sir.
Kaveri, Kavita, Komal, Mahadevi, Netra,
Present, sir.
Priyanka, Rohini,
Present, sir.
Sakshi,
Present, sir.
Sanket, Shruti Naik,
Sir.
Shweta Patil, Soumya Patil,
Present, sir.
Sujata,
Present, sir.
Vidyashri, Vishwajit, Mayuri, Shruti Patil,
Yes, sir.
Snehal. Okay, see this WI is nothing but it is a new weight what we got after updation. It means that already some random weight was there and we are just modifying that weight and now we are getting one new weight. That's all. And what this delta WI actually? That delta Wi is nothing but one more small equation you need to remember, that is eta into t minus o into xi. Okay, so eta, this symbol is called as eta into t minus o into xi. And regarding these all notations, eta, t and o, these all things we will discuss in next class. Okay, just t is nothing but it is a target output. Okay, o is nothing but it is a perceptron output. Try to make a differentiation. T is a target output, o is a perceptron output. That's all. And eta is a constant. So in the next class I continue with these notations eta, t, o and all those things. Whatever I explained today, you just go with that, you revise it, otherwise you never remember these all things because so many technical words are here. Okay, actually very easy concepts are there. The only thing is you have to remember these so many technical words, new words. That's all. Okay, okay, you can leave the meeting now.